All right, let's go ahead and pick up our discussion with molecular geometries. So whenever we start to discuss going from 2 dimensions with our Lewis structures to 3 dimensions using the Vesper model, we have to take a few things into account. So the first thing we do is we start to account for those valence shell electrons and the repulsion that they have. So whenever we set out to draw a geometry, first thing we want to do is figure out the Lewis structure. So whenever we draw a Lewis structure, let's say we had CH4, for example. Okay, so we have a carbon with 4 hydrogen atoms bonded to it. The first thing that we're going to do is we're going to start by determining how many electronic domains are around the central atom. So whenever we're counting domains, we're going to count single bonds as a single electronic domain. So for CH4, we would have 4 electronic domains. Now, if we had something with lone pairs on it, let's take, for instance, water. So H2O, where there's 2 lone pairs on the oxygen. We already said that we'd count the single bonds as 1 domain, but we're also going to count lone pairs of electrons as a domain. So water has a total of 4 electronic domains. Well, what if you have a multiple bond? So for instance, let's say we're looking at oxygen. So oxygen is a homonuclear diatomic. We want to figure out exactly how many electronic domains are around it. Well, we already said that we're going to count the lone pairs as 1, so there's 1, 2 electronic domains. So even though this is a double bond, we're still going to count that as a single electronic domain. So around oxygen there are 3 electronic domains. Let's go ahead and take, for example, nitrogen, that homonuclear diatomic. Well, count the lone pair as 1 domain, then the triple bond also counts as a single domain. So there are only 2 electronic domains around the nitrogen. So by counting the number of electronic domains, this will enable you to predict your geometric arrangement of the electron clouds, whether it be a bond or a lone pair, around the central atom. And that will help you predict the shape in 3 dimensions of your Lewis structure. So let's go ahead and take a look at some other notation. So you won't always be able to see a 3D model. So sometimes the way that 3D models are represented is that we have different types of bonds. So we use a line to denote that it's in the same plane as the central atom. So here for CH2ClBr, carbon is right there, our central atom, and then we have a hydrogen atom off to the side and a hydrogen atom coming up. Those are both in the exact same plane as carbon. But then we have chlorine coming out of the plane at us. So chlorine we would represent with a wedge. And then since bromine is going into the plane away from us, we'd use a dashed line for that. Now you guys aren't going to need to have to be able to draw structures with this notation, but if it helps you visualize it in 3 dimensions, it might be worth learning to do. But you guys will not be responsible for drawing anything in 3 dimensions. All right, let's go ahead and start predicting some Lewis structures. Well, predicting the molecular geometries from the Lewis structures. Go ahead and get out your cheat sheet of the electronic domains in molecular geometries. You're going to want to make sure that you memorize this table for the exam on Tuesday. So let's go ahead and take a look. So for CO2, if we draw that Lewis structure, we'll see again that everything obeys the octet rule. Okay, so That's a good Lewis structure there. Everything obeys the octet rule. No formal charge. So if we wanted to figure out what this looks like in 3 dimensions, we could look at our chart. So the first thing we want to do is count the number of electronic domains. Well, as we look at this, there's 1, 2 electronic domains around our central atom. So that means it has sp hybridization, which we'll spend a little more time talking about hybridization in a future lecture. But we can tell that this has a linear orientation. So this bond angle, that OCO bond angle, is 180 degrees. So this tells us it has an electron pair arrangement or an electronic geometry that's linear. And since there's 0 lone pairs, the molecular geometry is linear. So this is pretty easy to visualize. It's just a line of atoms. So go ahead and try to draw nitrogen by yourself. Make sure that you see that there are 2 electronic domains with 1 lone pair. Okay, so now let's move on to our next example, CH2O. So whenever you're drawing this Lewis structure, of course, the first thing you're going to do is count the number of valence electrons. So 4 from carbon plus 2 from the hydrogens, that's 6, plus another 6 is 12. So we start by drawing our Lewis structure, draw the skeleton, CH then we put in our single bonds. Okay, so then we complete the octet on the oxygen. All right, so we used up all the valence electrons. But this isn't a good Lewis structure because carbon does not obey the octet rule. So let's go ahead and look at the formal charges. So oxygen right now has a formal charge of -1. Carbon has a formal charge of +1. So to minimize the formal charges and to make everything obey the octet rule, we can add a double bond there. Okay, so now we have a Lewis structure that looks like this. So how many electronic domains are around the carbon? Well, each of the single bonds count as 1. And the double bond also counts as a single electronic domain. So there's 3 electronic domains, which I know is pretty surprising given the slide name. So if we have 3 electronic domains, it means we have sp2 hybridization. The bond angle is approximately 120 degrees. If all of the atoms coming off the central atom, if all the terminal atoms were the same, it would be essentially 120 degrees, but since they're slightly different, it's going to be around 120 degrees, but because of this excess of electron density here from the double bond, this HCO bond angle is probably going to be slightly greater than 120 degrees. But just for right now, let's just go ahead and consider this bond angle to be approximately 120 degrees. Think about it. You have 3 things coming out from that central atom. They're all in the same plane. So 360 degrees divided by 3 is 120 degrees. So there's no lone pairs on this molecule or on the central atom. So that means that the molecular geometry is trigonal planar. So another question that we could ask on an exam is how many sigma bonds are present? Sigma bonds means that there's single bonds. So for sigma bonds, you count every single bond as 1. So there's 1, 2 here. But then for double bonds, you count the first bond as a sigma bond. So in this structure, there are 3 sigma bonds. But then if we're counting the pi bonds, then there'd only be 1 pi bond. It's the second or the third bond in a multiple bond. So double bonds have 1 sigma, 1 pi bond. Triple bonds have 1 sigma and 2 pi bonds. So that's another type of question that we could ask you about what kind of bonding is going on. And we'll talk about that more later whenever we discuss hybridization. Let's go ahead and draw the Lewis structures for SO2. In this case, let's go ahead and have sulfur follow the octet rule. You should find there's 3 electronic domains, 1 lone pair. It has a bent geometry. Then whenever you draw your homonuclear diatomic oxygen, should find there's 3 electronic domains with 2 lone pairs and a linear geometry. So just double check that you can do that on your own. Okay, let's move on to CH4, methane. So let's go ahead and draw the Lewis structure for that. We have 8 valence electrons. So as we draw that, should have 4 single bonds to all the hydrogens. So methane has 4 electronic domains, which gives it an sp3 hybridization. And when we think about what this looks like in 3 dimensions, remember what we looked at in class. It looks like you have a central atom here, and then there's 3 legs coming off like a tripod, and then something coming off the top. Okay, and this is a tetrahedral arrangement. So the bond angle between any of these bonds that you choose is 109.5 degrees. So a common question that is asked is, would you expect the HOH bond in water to be 109.5 degrees, greater than 109.5 degrees, or less than 109.5 degrees? Well, because of these electrons, remember it's valence shell electron pair repulsion. Those lone pairs of electrons are going to repel one another, which are going to push these hydrogen atoms in just a little bit. And whenever they push in, that means that this bond angle is going to be slightly less than 109.5 degrees. All right, so let's get back talking about methane. So we said that there's 4 electronic domains, and it has this tetrahedral arrangement. There's 0 lone pairs, so its molecular geometry is tetrahedral. If you go ahead and draw the Lewis structure for NH3, ammonia, you should get 3 single bonded hydrogens and then a lone pair on the nitrogen. So again, there's 4 electronic domains, gives it sp3 hybridization, but this time, since there's 1 lone pair, instead of having a tetrahedral molecular geometry, it's trigonal pyramidal. So if you look at this, you can tell that this is a triangle-based, and then there's a pyramid. So it's a triangle-based pyramid here. Go ahead and draw the Lewis structure for water and hydrogen chloride, and you should see that both of those have 4 electronic domains and then 2 and 3 lone pairs, respectively, which gives them molecular geometries of bent and linear. So moving on to 5 electronic domains, this is whenever we start to see expanded octets on those central atoms. Let's look at phosphorus pentachloride, so PCl5. So whenever you're counting up your valence electrons, we have 5 from phosphorus plus another 35 from the chlorines. So you're going to draw this Lewis structure. You're going to start to draw these 5 electronic domains that look something like this, okay? So then we've used up all of our valence electrons. So there's a couple points that we want to make here. Whenever we're looking at 5 electronic domains, we like to break it up into 2 parts. We like to think about it as the belt, the equator there, and then our axes. So around the belt, if you took away these 2 atoms on the axes, the belt looks just like a trigonal planar arrangement. So we'll see bond angles between all these of approximately 120 degrees. But whenever we add in the 2 atoms on the axes, now we start to have this triangle-based pyramid again. But now there's 2 of them. There's one that's going up and one that's going down. So that's how this gets its arrangement name of trigonal bipyramidal. And whenever you have no lone pairs, like the case here, its molecular geometry is also trigonal bipyramidal. If you have 1 lone pair on here for SF4, this will bump the molecular geometry to seesaw. This is the hardest one for me to remember. And then if you have 2 lone pairs, like over here, on chlorine trifluoride. This is going to give you a T-shaped geometry, and then I would really recommend drawing out the Lewis structure here for I3-. Make sure that the terminal iodines here, they follow the octet rule. Your central iodine is going to have an expanded octet. But make sure you can draw all those. Try to visualize what these look like in 3 dimensions. Finally, let's go on to 6 electronic domains. So this is whenever you have an octahedral arrangement. So for octahedral arrangements, you have 6 coordinates coming out from that central atom. So here we have 4 coordinates around the belt. So this is a square planar arrangement. There's 4 things coming out from that central atom. Their approximate bond angle is 90 degrees. And then we have 2 atoms coming out of the axes as well. Okay, so we have bond angles between everything in that equator of 90 degrees. And then from the axes to the equator, it's also 90 degrees. If you have no lone pairs, it's octahedral. If you have one lone pair, this is the case on this compound, this is what is known as square pyramidal because you still have a square base, but now we have a pyramid. Then finally, if you have 2 lone pairs, it kind of makes a sandwich here like this with the xenon tetrafluoride. So you have the square planar arrangement, but then the axes are replaced with lone pairs. So you have a total of 6 electronic domains, gives you an octahedral arrangement, but the 2 lone pairs give you a square planar geometry. Okay, so that should get you through all the molecular geometries. Let's go ahead and continue our discussion on polarity a little bit. So whenever we talk about molecules being polar or nonpolar, we've talked about whether the bond itself is polar or nonpolar earlier. So the common example we might use is HF. We know that there's quite a large difference in the electronegativities of these atoms, so we would call this bond polar. Okay, and we represent a shift of the electron density with an arrow pointing towards the more negative species with the partial negative charge, and then putting a line through it here. It's known as a crossed arrow. So this crossed arrow, we cross it towards the positive atom here. So for HF, fluorine is the more electronegative atom. So the electron density is going to shift over towards the fluorine. It's not shared evenly. So this would be an example of a polar molecule. Anything that's a homonuclear diatomic, like oxygen, hydrogen, nitrogen, things like that, these are all non-polar molecules because they share the electron density evenly. So then the question we have to ask ourselves is, if you have a polar bond that's present, so then now we're going to consider a molecule with a central atom, so there's more than one terminal atom, does the molecule have a dipole moment? Okay, so water is a fairly straightforward example because the way that we draw the dipole moments on this is, well, is oxygen more or less electronegative than hydrogen? Well, it's more electronegative. Okay, but then what do we do with the lone pairs? Okay, well, whenever there's a lone pair, we are going to draw this dipole going away from that central atom towards the lone pair. So in this case, as we look at all the dipoles on water, none of them are canceling out. So we end up with a net dipole that looks like this. Okay, so in this case, there are polar bonds and the molecule is polar. Okay, so let's look at an example when we have polar bonds and maybe it's nonpolar. Okay, so here's an example of cis dichloroethylene and trans dichloroethylene. So let's go ahead and draw in our dipole moment. So we know that chlorine is more electronegative than carbon. And carbon is more electronegative than hydrogen. So overall, this molecule has a net dipole going up because they are not canceling out. Now let's look at trans dichloroethylene. Here we have dipoles that are pointing away from the carbon towards the chlorine and towards the carbon from the hydrogen. Well, how can you tell what's going on with the arrows? It's really hard to tell in 2 dimensions. So remember that each of these carbons has a trigonal planar geometry. So in this case, all of the atoms are in the same plane. So you can tell on cis dichloroethylene that there's a net dipole going up because the 2 chlorines are pulling towards them. There's an electron density shift towards them and then towards the carbons. So there's going to be a net dipole going up. But then for the trans dichloroethylene, the chlorines are each pulling this way and this way, and those forces are going to cancel each other out. And then both the carbons and the hydrogens are both pointing in towards each other. So those are going to cancel each other out. So overall, there's no dipole for this molecule. So it is possible to have polar bonds and still be nonpolar overall. So cis dichloroethylene is polar. Trans dichloroethylene, nonpolar. Let's look at a few more examples. Let's look at H2 versus HCl. All right, well, the first one, that homonuclear diatomic, the electrons are going to be shared evenly. So we would call this one nonpolar. Now HCl, we know that chlorine is more electronegative than hydrogen. So there's going to be a shift, the electron density towards chlorine, and then you don't really need to draw all these electron pairs with those dipoles pulling out, but you can. So as we look at this, you can look at chlorine and say, okay, well, there is a tetrahedral arrangement around the chlorine, but then there's only one bond to it. So overall, there is a net dipole, and it is going to be going this way. So this molecule is polar. Well, what about BF3 versus BH3? So here, each of these molecules have a contracted octet. Okay, so we know that fluorine is more electronegative than boron. So this has a trigonal planar arrangement. So that means that all the dipoles and those polar bonds are going to cancel each other out. What about BH3? Well, maybe we should look up in our electronegativity table what the electronegativity of boron and hydrogen are, because I sure don't remember off the top of my head. So, boron and hydrogen are essentially equivalent. Hydrogen is slightly more electronegative. It's 2.1. So again, all the dipoles, there would be a very, very small dipole pointing towards the hydrogen, and they would all cancel each other out. It is possible for everything to be pointing in and to cancel each other out. So for example, if you had methane, so CH4, so trying to visualize this in 3 dimensions. Carbon has a tetrahedral arrangement. All the dipoles are pointing in towards it. So whether they're all pointing in, they can cancel out, or if they're all pointing out, they can cancel out. So the last Lewis structure we'll consider is carbon tetrachloride and then CH3Cl. So here, as we look at this, we know all the chlorine atoms are more electronegative than carbon. They all have 3 lone pairs around them, so there's going to be a dipole pointing towards each chlorine. So these will all cancel each other out. So this molecule will be nonpolar, whereas CH3Cl all the hydrogens are pointing towards the carbon. So if you think about this being the tripod of the tetrahedral, and then we have a dipole pointing towards the chlorine, we're going to have a net dipole going this way, and that molecule will be polar. So how can you start to guess quickly what the polarity of a molecule is? So a few hints that generally work is your molecule is polar if you have 1 lone pair of electrons on the central atom. It can be close to being nonpolar. It depends on the electronegativities of the other terminal atoms, but 99% of the time, 1 lone pair of electrons means that you're polar. If you have different terminal atoms, like we did right here with CH3Cl, that's going to indicate to you right away that that is most likely polar. Okay, well, what about nonpolar cases? Well, if all your terminal atoms are the same and you have no lone pairs, you're nonpolar. If you have multiple lone pairs that cancel each other out, then you could be nonpolar as well. The best examples of this would be the xenon tetrafluoride. So remember, this one has 6 electronic domains. Each of the fluorine atoms has a filled octet, but then there's 2 lone pairs on that xenon. So if you were to go through and draw in all the dipoles, because all the fluorines are in the same plane, they're going to cancel each other out. This fluorine is going to cancel that fluorine. Those dipoles will cancel out. This fluorine is going to cancel out that fluorine, so those dipoles will cancel out. But then the lone pair pulling up and the lone pair pulling down, those will cancel each other out. So that's a nonpolar molecule. Another example would be I3-. This one's a little harder to visualize. So each of the terminal iodines obey the octet rule. The central iodine has 5 electronic domains, 3 lone pairs, so it has a linear molecular geometry. So this iodine bond here and here, those are both nonpolar because it's bonded to itself, so they have the same electronegativities. But then all these lone pairs, they're around the belt. So it has that trigonal planar arrangement. So they all cancel each other out. So overall, I3 minus you would expect to be nonpolar. All right, well, I hope that helps you get caught up on everything, and we will review some more on Monday.